Okay, welcome back to lesson 29, continued practice with the power series. Let's dive right into this example. Find the radius and interval of convergence for the series and determine where the series converges absolutely and conditionally. So here's the original series. You can see I've already cooked up the ratio test, the beginnings of the ratio test for us. So you'll notice that I took, n plus 1, store in n plus 1 in place of n. So we have x to the n plus 1 over 1 plus n plus 1 squared. And then basically multiplying, I'm just mapping this out for you, multiplying by the reciprocal of the original expression. So we're running the ratio test. Let's clean that up a little bit. I'm using Explain Everything on my iPad to do this video. So you'll notice that this cancels with this, and you're going to be left with just an x up top. So once again, the gathering of what you're left with. Downstairs here, we're going to want to expand that out. So you're going to have n squared plus 2n plus 1 plus another 1. So that's basically going to lead you to n squared plus 2n plus 2. Okay, all of that. And then obviously you're left with this expression as well, so times 1 plus n squared. Okay, now what I'm going to do is, let's scoot this on down here. Let's gather that last expression. And you're going to see I'm just going to kind of rearrange it a little bit because I'm interested in the limit as n approaches infinity. I'm just going to kind of extract these pieces here. So, meaning the terms that have the n's in them, kind of keep them together. Over n squared plus 2n plus 2 times x. Okay. Well, we're interested in the limit as n approaches infinity, so by now you know the degree of the top is the same as the degree of the bottom here, so this whole expression is going to tend towards 1. So that's going to lead us to basically the absolute value of x. Well, we know way back from the geometric series then that this will converge. So we know that we converge if absolute value of x is less than 1. Okay, so let's just kind of take it from there on the next slide. Okay, so sorry, I'm getting used to this recording device. But remember, if we go back to that original slide, we were told to find the radius and interval of convergence for the series and determine whether the series converges absolutely and conditionally. So we did. So if we converge, if absolute value of x is less than 1, that really means negative 1 is less than x, which is less than 1, is our interval of convergence. So we were looking for that interval of convergence, but remember though, and I'll highlight this in red, that we haven't tested the endpoints yet. Note to self, test endpoints. All right. So, because we may have, conditional convergence, or perhaps absolute convergence at those endpoints. So, test endpoints, and let's start off with x equals negative 1. Well, if we do that, store negative 1 into the original series, and you're going to have negative 1 to the n over 1 plus n squared. Well, if you kind of take this and put it in absolute value, right, because that's an alternating series, so then you're interested in the series 1 over 1 plus n squared and how that behaves. Well, 1 over 1 plus n squared, we could show that that converges by, when the limit comparison test is used. We're going to see the limit comparison test more formally when we do the next endpoint. But for now, let's just note it. Converges when LCT, limit comparison test, is used. So converges absolutely by the AST. So note to self, so at this endpoint, converges absolutely by the AST. All right. Now, on the next slide, let's test the other endpoint. Now let's test x equals 1. We'll store 1 into the original series, and you're looking at 1 over 1 plus n squared. And remember, we had mentioned the comparison test before, the limit comparison test. So now, actually, I didn't write it out before, I just said it, but now I'll actually write it out. So let's compare it to summation 1 over n squared, which is a known convergent p-series. Okay, and remember how the limit comparison test works. You want to take the limit as n approaches infinity of the original guy, 1 over 1 plus n squared, over the guy you're comparing it to, the known convergent, so 1 over n squared, right? So if we clean that up, that complex fraction, we will arrive at the limit as n approaches infinity of n squared over 1 plus n squared. And clearly that's equal to 1, which is greater than 0, because you remember the limit comparison test makes you, has those stipulations, so we arrived at a constant that's greater than 0. Therefore, we have absolute convergence by the limit comparison test, and really the absolute convergence test. So once again, we have absolute convergence at that endpoint. So that little triangle is therefore. So therefore, we have absolute convergence by the limit comparison test and the AST. All right, so after all that sweat equity, let's summarize. So all of that, testing the endpoints and all of that, led us to this. So originally, the interval of convergence was -1 to 1. But now, what we've discovered after testing the endpoints, and so I want to get you really comfortable with this language, and you'll see it in all the textbooks, absolute convergence from -1, which is less than or equal to x, which is less than or equal to 1. So notice those less than or equal to inequalities. So therefore, the radius of convergence is 1, and therefore the center is about x equals 0. So it's centered about x equals 0. And note to self, no conditional convergence. Because remember, we were told at the beginning, and I want to go, and voila, there you have it, folks. I don't want this video to be too long, so I will do yet another example on another video. Good luck out there.